Speaker tonight is Dr. Aaron Clevenson. He is a well-known member of the astronomy community in Houston. Aaron is the Observatory Director of the Insperity Observatory in the Humble ISD. He has held that position since the inception of the observatory in 2009. He's also been an astronomy professor at Lone Star College in Montgomery, where he taught solar system and stellar astronomy classes for 17 years. He is an observing program director with the Astronomical League. The HAS is, for the newer members, belongs to a national organization called the Astronomical League. So when you're a member of HAS, you're automatically a member of that. And there are 17,000 members to that, like our clubs. So he's a director of some of those programs. In this role, he works with the coordinators of the more than 70 different programs that are available, 5 of which he created. And Aaron is an officer and past president of the North Houston Astronomy Club. So he's a local, he's been around for a while, and I've known Aaron for a long time. So now I'm going to hand it over to Aaron.
Good evening, everyone. So good to see you all, and so good to be back with HAS again. Tonight's presentation is Webb's first look at the universe. This is a presentation that NASA put together and distributed to a number of sites, actually only 27 of them in Texas. And this was for the great, announcement. These are our first images. And unfortunately, we did the presentation before the images were even available by about 3 days. So I have modified the deck. It now includes those images, and I'm sure you all have seen those images because they're everywhere. And it's so spectacular that I think pretty much everybody has seen it. So let me just dive in with both feet. What we're going to do is we're going to talk a little bit about the background, taking off, launching the James Webb Telescope, talk a little bit about why this telescope is so special, specifically infrared light, talk a little bit about what they intend to do with it, and then what exciting discoveries they're going to most likely make and what ones they have done. So we'll just talk about them as we go. And I'm fairly informal here, so I don't know how you want to do this, Steve, but I'm willing to take questions pretty much at any time. Okay, so before launch, there were a few things that happened. So back in 2016, they were working on testing all of the optical elements. Many of us remember when they sent Hubble up, it had an optical problem, and they actually had to send it a pair of glasses to make it be able to see the way it was designed to see. Once they did that, it saw some pretty awesome stuff. This time, they wanted to make sure that did not happen, so they were much more thorough in their testing. They finished that. 2017, they finished testing it with the integrated science instruments. And they started testing the spacecraft and sunshield. So all of this stuff was going on behind the scenes. In 2018, October, that was the initial planned launch date. And no kidding, it did not happen. December of 22, a new launch date after 5 missed ones in the meantime. And that didn't happen. December 22, still working on it. December 24th, that was their next one after that. And the problem was in the 22nd, they were having communications issues. And so they had to solve those before they could launch. And finally, after another day's worth of weather delays, on December 25th, that's kind of a Christmas present for everybody, they launched. And it was exciting. It was a very exciting launch. In the pre-dawn hours of Saturday, on the 25th, everybody was looking to see this launch. Now, that's not quite true because, sadly, it was being launched from French Guiana, in South America, so we didn't get to see it from here. However, it was very exciting, and actually, I can share that excitement with you. Maybe. Oh, that's not what I did. Let's try this again. Let's see if this works.
Aaron, we're not hearing any sound.
You can't hear that?
No.
Oh, Well, we'll just watch then. Sorry, don't know how to make that happen.
Aaron, do you have a lot of videos? If so, there's a way to get the sound to come across to us.
Well, now I stopped it. That was not good. So this is obviously an automation.
Just amazing how they can fold that thing up like that and get in there and then origami it out to be so big.
Yeah, it was quite a puzzle putting that all together, and every one of those little pieces had to work. Okay, I'm going to cut that off. And the reason for that is it goes on a bit more. And then it gets to this piece. This is actually a picture from the rocket body. And this is the last direct images of the telescope as it moves on its way. So just back up a little bit here. It's the world's largest and most complex space science observatory. It's going to study infrared light from celestial objects and in slightly different wavelengths than we've studied in the past. So we can think of it as the successor to Hubble, but it's also a successor to the Spitzer Space Telescope, which was an infrared telescope. And as some of you probably know, I'll repeat just for anyone who doesn't know, the reason we want to study infrared light is infrared light can go through dust and gas that visible light will not be able to penetrate. So we know radio waves do that, but infrared light does it as well. The difference is to get really good infrared information, you have to have your telescope in space. So it took off, everything was perfect. 27 minutes into the flight, they separated, and we're going to try this video. This should be a short one, and so it should be interesting. And I'm sorry you can't hear this video either. It's playing mostly music. So this was separation from the rocket. What's amazing to me is they can get these pictures. So what we're seeing here is one of the, one of the solar panels deploying. And once it has deployed both solar panels, then it can actually run on solar power, which is where we'll get most of its power from. And I'm going to cut it there. again, just, you can't hear the cute music that NASA put in there. So I'm just going to let it go ahead. This is a diagram that shows the process by which they are opening everything up and, making it so that the entire telescope can do what it's designed to do. So if I start up here at the top, it left Earth, left its rocket behind, opened up the solar panels, and actually put the telescope up, which was in the middle. And then once that's up, the next phase was the deployment of the sun shield, which, seems like it ought to be simple, but unlike a lot of our equipment, it's not just one shield. This is actually a number of layers. And each one of those layers lets it get cooler and cooler and cooler, in essence, further away from the heat of the sun and the Earth and the moon, until you end up with this picture over here where they're basically all deployed. They actually have little springs and wires that separate them so that you get that, I was going to call it airspace, but I guess it's space in between them. Once it's up, then they move on and they actually put up the secondary mirror support, which are this tripod that the secondary mirror is on. And then another piece that I just find totally amazing is, if you look at this next picture, the side panels of the telescope, because there are 18 segments, but in order to launch it in the rocket, they had to fold some of those segments back. So they then brought the wings out. And then once those wings are in place and locked in place, then you have a fully deployed telescope. So this process was all going on as it was moving towards its new home, which is the L2 Lagrangian point. So every two-body system, in this case, Earth, Sun, has 5 Lagrangian points. The one that's most useful in this case is L2, which is on the opposite side of the moon. And it actually is way out there. It's about 1 million miles away from home. And I'm going to just bring up the other one. Another way to look at it here is we launched it and went out here. And in that journey, which was 5 months long, give or take, during that time, it was doing all this on deployments. Once it was fully deployed, then they started testing equipment. But the thing about this is, unlike the Hubble, which we could actually go service, at least initially, there's no way to service this telescope. If anything goes wrong, that's just it. It's down. And so there were lots of pieces that had to be tested, and they were very thorough about that because there aren't very many backups. When we do human spaceflight, there's backups for backups for backups. But in this case, because of the need to keep it as light as possible, there just wasn't a whole lot of opportunity for those backup systems. So it got out here, it's out past the moon, and it ends up in this elliptical orbit that you can see here around the Lagrangian 2 point. And the reason for that orbit is twofold. One is, if it ever were to go behind the moon, we would lose communications with it. And also, if it's behind the Earth or the moon relative to the sun, it would not be getting light on its solar arrays. So it's really important that it has an orbit that's just big enough to take it outside of those bodies so that it can see the sun, so that it can see the Earth at all times. Okay, so a look at this. It's just amazing to me that this all worked. I'm going into all the details here. But you can see it's a pretty amazing telescope. The top part of this picture is the piece that is going to be looking at objects, where they're going to be looking in the infrared. Then you have the heat shield, and then most of the equipment, the instruments, are all on the backside of that heat shield for two reasons. One is they don't need to be cooled off as much as the telescope does. And they do generate heat, and you don't want that heat anywhere near your infrared telescope either. So all that's on the backside. And no, let's just move on. So this is an image that shows all of the different countries that were involved in the partnership. You can see the US, of course, playing a major role in that, but Canada and Europe and Australia are also, and Japan, I shouldn't leave them out, are also major partners. And this is not only the people who put it all together, but it's also the scientists that are planning on using this and gathering information from it. So very big deal, involves just about most of the world. And it's kind of amazing. Hold on just a second. I'm trying to catch up on my notes here because I haven't been following the notes. All right, we're going to just keep going. So if you take a look at this, and I alluded to this a little bit, but I'll talk about it a little more. On the, we'll call it the outside of the telescope, you have your telescope itself. These mirrors, the 18 segments they're hexagonal mirrors, and they're designed so that when you get them all tuned properly, they act like one gigantic mirror. And we'll talk about that in a little bit. And of course, like every telescope, there's a secondary mirror. And the reason the primary is gold reflects infrared light much better than silver. And so they are actually gold plated. That information then passes through the multi-layer sun shield to where the instruments are. And the instruments, many of them are down here on the bottom. So there's a star tracker. Obviously, if you're using a telescope and it's not fixed, you don't have the problems of a fixed telescope, but you do still need to make sure that you're still pointing at the same object throughout the run. And so they've got very sophisticated tools that they use for tracking stars. There's, of course, the solar array and the antenna that it uses to communicate to Earth. And then it's got to be able to change its attitude just a little bit so it can point to different objects. So there are some steering and control units, and all of that's on the backside, or the, let's call it the inside of the telescope, the parts that aren't actually doing the infrared observing. Okay, so on the back, I'm not going to talk about all of these in great detail, but I'll talk a little bit about it. If you take a look at the instrument package on the back, there's a couple pieces that you may hear people refer to. So there's this NIR and also the MIR pieces. NIR stands for near infrared. So over here on the left is the near infrared spectrometer. And over here is the near infrared camera. MIR stands for mid infrared. And so there's a let's try that again, a mid infrared capability as well. So it can actually expand to cover two pieces of the infrared spectrum. And we'll talk about exactly what we get from that in a little bit. But the Hubble did visual and some of the near infrared. So this one goes much further into the infrared than the Hubble did. Okay, so here's a better picture that shows that orbit I was talking about. This is not to scale at all. It should say that somewhere on here. I don't see it. Because the Earth is here. The moon is orbiting around the Earth. And way, way out here is the L2 Lagrangian point. And so, as I mentioned, the telescope is actually orbiting in an ellipse. But because it's in that L2 point, as the Earth moves around the sun, the telescope will also move around the sun. And so it works out really well for being able to get really, really dark and cold telescope so that you can actually look out there. A little bit of information up here. The injection burn that was to put it into its orbit was February 2nd of 2022. And of course, this can't be right because it's backwards. I have no idea why that says January. I imagine that's supposed to say February as well. Okay. And I did this for the folks who are saying, he keeps talking Lagrangian. What's he talking about? So these are the Lagrangian points. This is the Sun-Earth system. Of course, the Earth-Moon system has our own, but that's not important here. So you have the Sun, and between the Sun and the Earth, you have Lagrange point 1. Outside the Earth, you have Lagrange 2. And on the opposite side of the Earth, where some conspiracy theorists believe there could be another planet or perhaps an alien spacecraft out there. Actually, it is just a counterpoint for where the Earth is. As far as we know, there's nothing in it. And we do have spacecraft that are out above and below the sun, so we can actually see that point, and there's nothing there. And then 4 and 5 are stable points that are in front of and behind the Earth in the Earth's orbit. And although we don't have any asteroids that are hanging out in L4 and L5, some of the planets do, especially the larger planets. because it's also a stable point where it's pretty easy to stay there and not get knocked out because of the Earth or the sun. All right, let me keep going. So we launched it. We've sent it out there. The people who are talking to the telescope are the Goldstone, California antenna, the radio telescope out there. And it's actually being controlled from Baltimore, Maryland. I think that's Goddard, but I'm not really sure. That's where they control most of the spacecraft. So those are the two pieces that are involved. And of course, the telescope's out there. And the symbolism here is taking pictures of these really cool galaxies and things in the infrared. Okay, so here's the telescope mirror. And over here, we have a typical person. We'll pretend that's Joe, since he's not on the call, right? We can pick on him. So this is Joe. And if you look at Hubble's mirror, it's bigger. It's a really good sized primary mirror, bigger than a person going across, and then compare it on the same scale to the 18 segments of the James Webb Telescope mirror. And you can see it's sizably larger. And we all know, because we all like telescopes, that the bigger the mirror, the bigger the telescope, the more light you gather. And the more light you gather, the fainter things you can see. Or conversely, the more things you can see, because now you can see fainter ones. And so this mirror, huge mirror, can see lots of detail. And like I said, originally when I gave this talk, it was 3 days before we got the first picture publicly. And so we didn't know what it was going to look like. And I've got the pictures that I've included in this talk so we can actually compare and see how cool they really are. So grand total, it's 21, almost 22 feet across. And comparing that to Hubble, which is about 8 feet across, so a little bit bigger than a person. I mentioned it was coated with gold. The gold is 1,000 atoms thick, so they were going cheap on the gold, but that was enough to give them the reflective surface they needed. And and we'll talk about the first light as well. I think that's the next slide, actually. So this is the honest to goodness first light image from the telescope. And in this image, I didn't put the second one in, but in this image, you can see what should be 18 fairly bright. And if you could look at them spectroscopically, you would determine that they are identical stars. In reality, that's one star. But just like you have to align and collimate your telescope, they have to do the same thing here, except they have to do it 18 times. So each one of those 18 segments have to point in such a way that that star's light hits a particular pixel, probably not exactly one, but a particular pixel on the focal plane. So when you capture it, that's what you see. And when we get to the next slide, I will make a few more comments to go with that as well. This is the result of when you get them all aligned. So this is not even a legitimate picture. This is just, we're working on setting up the telescope. And I look at this and there's galaxies everywhere. It's just amazing to me. And this isn't even, a big deal picture. So I have one other thing to mention here. If you looked at the Hubble telescope deep field images, you'll notice that the stars had 4 spikes. And the reason for that is there are 4 vanes holding up the secondary mirror in the Hubble telescope. This one has 6 spikes. And the reason it has 6 spikes is they're hexagonal mirrors. And each edge of those mirrors, since they can't match up exactly, creates a diffraction pattern. And so that's where we get the 6 from. What I have not figured out is where the one that goes through the middle is coming from. But that's okay. But anyway, this is the first real fully aligned image they get back from the telescope. And I don't know about you, but that's better than anything I've ever taken. So I'm impressed. So the real question is, why are we doing this? I mean, we had the Hubble telescope. The Hubble telescope was pretty awesome. And the question is, why? And the problem is what we can see versus what we can't see. So if you think about it, and this thing over here on the right is supposed to resemble that, I think. But the idea is we see in visual light. And if you look at the whole electromagnetic spectrum, that's a tiny, tiny little piece. And in reality, there's a lot out there that the human eye can't see. And so we want to see more of that because every different part of the spectrum tells you different information about the thing you're looking at. So we've done radio telescopes here on Earth for a while. The problem with radio telescopes is they're big, they're heavy, so you don't want to launch them into space. And they work perfectly well on the ground because a lot of the radio waves make it all the way to the ground, which means we can detect them full strength. They don't care about clouds and rain and all that good stuff. So what we want to do is come up with a telescope that goes outside of that. And the Webb telescope detects near infrared and mid infrared wavelengths. So if you think about the spectrum, right, it goes from violet to red. That's what we can see. And then if you go past what we can see with our eyes, you get to the near infrared, mid infrared, far infrared, and then you go into the microwaves and radio waves. So that's where we want to go. We want to see a piece of that we can't see really well from here on Earth. And here's an example of why. The pictures on the left, those are meerkats and we'll just call it an alligator since we're in Texas, right? Okay, an alligator. And that's all fine and good. That's what we see when we see them. But in infrared, you get other information. So if you look at the picture on the right, you can see, well, one thing is it seems to be reacting to heat. So mid-infrared, although it's not heat, it behaves a lot like we think of as heat. So you see right here, the meerkats are glowing pretty bright. And that's because, right, they're warm-blooded animals. Yeah, they're hot little critters. And so the background tends to blend in. We can't see the leaves. We can't see all the details. But hey, we sure can see those meerkats. And if you look over here at the alligator, you see the same kind of thing. You know, over on the left, we see, yeah, all right, he's there. I can see him and he kind of blends in, but not really well. But over here, we can see that the background is fairly cool. And the alligator, which probably was a little while ago basking in one of the hot pools, is now out here cooling off and going back towards that ambient temperature. So you can see it's very different information. And I mentioned this, but if you take a look at it, this visible part of the spectrum right here, violet to red, is right in here, this tiny little piece. And if you look at what the Hubble telescope could see, it could see a little bit into the ultraviolet and a little bit into the infrared. And that's really good, lots of good information, incredible pictures. But then if you take a look at the Spitzer telescope, you see, well, it basically covers the mid to far infrared. So mid would be in here, far would be over here as you're getting closer to the radio waves. And that was great and told us lots of information. We could see the center of the galaxy. You know, we can't see it, but we could see stars around the black hole in the center of the galaxy. But what we needed was to fill that gap. And so the James Webb Telescope starts here right at the edge of visible light and goes all the way down here, basically through mid-infrared. And so it gives us a whole range that we haven't had a really good view at. And of course, it's also the latest, greatest, newest technology, so ought to be better. All right, hold on. So what do we get? Well, if you take a look at this particular object, this is the Cat's Paw Nebula, for obvious reasons. And if you take a look at it in visible light, you see the one over here on the left. And this was taken by the European Space Agency with one of their telescopes, ESO. And okay, hey, looks like very typical emission nebula, right? That's hydrogen alpha light. Looks very familiar to us. But if you take a look at it in the near infrared, you get to penetrate some of that dust and gas. And now you start to see more and more stars, some of them that were completely obscured by the dust, but now we can see them. So that's what we get with the near infrared light. That's here in the middle. And you can still see where the nebulae are, but now millions of stars. It's just absolutely amazing because we're penetrating that dust and gas. Mid-infrared light, as I mentioned, it behaves more like heat than what we traditionally think of as light. And so if you take a look at the one over here, this is from the Spitzer. What we see is it's glowing because it has infrared light, and they use color the same way we would think of color. The lighter that color, so red, orange, yellow, actually probably moving up to green. As you move up that spectrum, you get different frequencies, just like we do in visible light. So here you can actually see what's going on inside those nebulae and behind some of the dark dust clouds that we can't see through. So it's just a really nice example of how the different wavelengths bring us different information. Okay, so we're out there and we're pointing out there towards space with the James Webb Telescope. And we talked about the advantage of seeing infrared, but why do we care about infrared? And I'm going to use an even more extreme example that many of you are familiar with, and that's the cosmic microwave background radiation. When that radiation was created, it was infrared. But because it is so far away, it's over 13 billion light years away, and the universe is expanding, the further away you are, the more redshifted your light has become. So that light we now perceive as radio waves, and we can pick that up with our radio wave telescopes. However, if we want to look at the very distant galaxies, the first stars that formed when the universe was very, very young, their light would have been way up there, probably gamma rays, X-rays, very high energetic light. But again, because they're so far away, the further away you go, the more you get stretched, and that light is now coming to us as infrared light. So that means we can see stuff that we would not be able to see because of its distance, because it's been shifted so far in the red direction. So it's just a really great tool for bringing us that which we couldn't have seen anyway. There are still limitations on how far you can see, but at least we can see further. Okay. So what kinds of information are we going to get? So this is a Hubble image on the left, and the spectrum we can get out of that image. And so when we look at it spectroscopically, we can see bright lines, and we can also see dark lines. The dark lines symbolize light, different wavelengths that have been absorbed, typically by chemical elements. And the bright lines show us the presence of those elements. And so depending on whether we're looking for the bright lines or the dark lines, it tells us information about the object we're looking at. And so when we're doing that, we can use spectroscopy. The really cool thing about this telescope is, and I'll give you an example. In the observatory up here in Humble, we have a spectroscope. We have a really nice spectroscope. It can look at one thing at a time. The Webb telescope is designed so that its spectrograph can look at multiple objects all at the same time. And so not only is it taking pictures, it's taking the spectra of each of the objects in those pictures. That gives us all that more information. And unlike the old days, we feed that spectral information into a computer and it tells us what's out there, rather than us trying to measure exactly how bright those different pieces are. Okay. So what are we doing? Well, the light comes in, it bounces off, it goes through a slit, bounces off a mirror, and then it gets broken down into those different wavelengths. And here you can see some of those dark lines. And this is not at all where I would expect the lines to be if I were looking at something that was nearby and therefore not red shifted or blue shifted. So when I look at these, they have been a little bit shifted. I can't even tell you which line is which because they've been shifted so much. But it lets us split that light. And hopefully we will be able to go way, way back and see light from very early on when the universe was very young and very new. Okay, I'm looking to just see if there's anything else I really ought to mention. I don't think so there. So let's take a look at what the universe will look like when we use the Webb telescope. And again, keep in mind, these pictures are not from the Webb telescope because we haven't gotten to that part yet, with the exception of the ones I showed you of that very first star that they were focusing on. Okay, so in the early universe, if you're wondering how did all this work, we're over here, present day. We've got a nice clear universe. We can see all the galaxies and stars, at least those that are bright enough and close enough. But prior to that, all kinds of stuff was going on, but we couldn't see it because of the dust and gas and the fact that electrons were zipping around everywhere. The universe was a mess. And so what they're hoping is we can go way back and we'll be able to see the stars just starting to form. And those stars, of course, will start clumping together just like matter does and forming galaxies. And because they become bigger and bigger as galaxies collide and merge to get us to where we are today. So by looking at different points in the past, we can get an idea of what the universe has done in the past. So that's the goal. Okay. So we do want to go out and look for some of these early galaxies. And so this is a galaxy from the Hubble Deep Field Image. It's 13.4 billion years ago. So it's 13.4 billion light years away, only 400 million years after the Big Bang. So that's almost as far back as we can go. And it is as far back as we can go almost visually. We can go back to about 380 million years. So it's really cool, but we want more. We want more information. We want to see what happened before these little blobs of galaxies actually were in the clear where the light could come to us from them. So it was a very different place. And what we want to see is more detail. And so to get that detail, this is an example of what we think galaxies have done over time. So they started like the one we just looked at, these little amorphous blobs. And as time goes on, they start merging, they start forming, they develop a little bit of structure. I can actually see the start of spiral arms here, which is kind of cool in this picture. And then they keep merging, and over time, they get more and more well-defined until you get to the galaxies that we have today. And that's what we want to see. We want to see galaxies that are so far away that they represent different stages in this evolution of galaxies. So that's the plan. That's where we're going with all this. And by the way, we'll have time for questions at the end, but I'm kind of skipping through stuff like you all know what I'm talking about. So if you have questions about something I'm saying, hold on to them and we'll get to them. Okay, so these are the galaxies. But the other really cool thing is, although it still can't see them, it will be able to see black holes and their environment around them in particular in much more detail. So this is an artist's rendering of what they think it's going to look like. And that's a wonderful picture. Hopefully now with James Webb, we'll actually be able to go in there and see detail of what's going on inside the dust balls that seem to block our view of most of the black holes. But again, we're not going to be able to see black holes. I did not say that. Okay. So this is where we hope to go with it. We're going to study things like quasars, which will be the earliest galaxies. We're going to study things like the black holes in the center of other galaxies, not just our own. And we can see how the black holes and the jets and all of those things over time, again, because we'll be looking at different points back in time, how that has affected the development of the galaxies. Right now, we have no real idea of where the spiral arms in the Milky Way galaxy came from. And so hopefully we'll be able to go back and say, okay, so this all happened along the way. This must be how it's happening. So lots of excitement, lots of things to come. So stars, there are lots of cool stars out there. You may recognize the picture on the left. Hubble has taken some really cool pictures of clouds. And inside these pillars of dust and gas are stars, brand new stars. They just were born. And they haven't yet built up enough stellar wind to blow that dust away. They will someday. But when you look at infrared light, and again, this was pre-Webb, so this is a Hubble infrared picture, you can see inside these pillars of dust that there's actually all kinds of stars in there being formed, baby stars. And so we can see stars that we would not otherwise be able to see. And so to me, that's just amazing. Okay, so this is all cool. But we also want to be able to detect details of what's going on out there. And so in addition to looking at chemical elements like hydrogen and iron and other stuff like that, by doing that spectroscopy, we can also detect molecules. And they've started doing that in just our local dust clouds as well. But now that we have a telescope that can see through some of this dust, we should be able to see even more information about molecules that are out there. So we should be able to see the physical and chemical properties of stars, planets. Those are extrasolar planets, by the way, and nebulae. We also should see lots of details on the spectroscopy of star-forming regions, which will be really cool. And what they expect to do is they'll look at different stars at different points in their lives. We'll be able to determine their size, their mass, age, color, temperature, what stage of evolution they're in, and just information on their environment where they're forming. So just lots of information. And in addition to that, on the other end of the star's lifetime, gas and dust ejected from dying stars, and even look out there between the stars for molecules. And who knows what we'll find. They've already found amino acids out there in dust clouds in the Milky Way. There's no telling what new molecules they may discover. Okay, so in addition to that, and again, this is not a Webb picture, but hang on, there will be one. But it also gives us a chance to look at objects in our own solar system. So there are some objects that are just in too close to look at. So if you think about it, the moon, the earth, the sun, obviously, Venus, Mercury, all of that stuff for the telescope is sunward. And the telescope can't look sunward. It's designed to be kept very, very cold, extremely cold. And so in order to do that, it can't look inward. It has to look outward. And so it will be able to look at Jupiter. It'll be able to provide detail like this. This is infrared light taken from the ground at the Gemini North Telescope. And it'll be able to show us this detail and more. So there's just lots of things that we'll be able to see from the planets. And we're hoping that that'll help us better understand what has happened in our solar system. What has happened to Mars, why it has no atmosphere or virtually no atmosphere. I mean, yes, it has atmosphere, but not enough. And then other things like asteroids and Kuiper belt objects. So there's just so much to explore out there and all this new information we're going to start gathering. And then, of course, extrasolar planets, planets outside of our solar system that are orbiting other stars. It provides us a way to find them. It provides us a way to do spectroscopic analysis of the atmospheres of those planets. And because of that, we can identify planets that may be more suitable to life, at least life as we know it. So absolutely amazing, incredible opportunities out there. And we think it can help us find distant planets. So this is an infrared picture. And yes, they've got an occulting dot that's blocking the star. The star is actually where that little star-shaped icon is. But by looking at that star and looking in infrared, stars don't glow as much in infrared. They glow a lot more in the visible and higher colors. And so in infrared, you can block it out. And what we see is 1, 2, 3, 4, and maybe more planets that are actually orbiting this star. And that's just so cool. So let me see if I can tell you about this one. So this one was taken at the Keck Observatory. So again, that's Earth-based. And of course, Webb's going to do things a little bit differently than this one. But the stars will not show up well in infrared. The planets will show up even brighter when you take a picture of them in infrared, because after all, that's what color or what part of the spectrum planets glow in. It's going to have huge mirrors, capture longer and much deeper infrared light. And so we're going to be able to see all kinds of information we couldn't see otherwise. And let's see. All right, that's all I'm going to say on that one. All right, so we look at these planets. We're going to see a planet that's going to move in front of the star. And by comparing the star's spectra without the planet and then the star's spectra with the planet, the equipment is so sensitive they can subtract out that star. And what you're left with is the planet's atmosphere and the spectroscopy of that atmosphere, the spectrum. And so here's an example of what that might look like. When you get rid of the star, you're left with a baseline. And we can tell that some of these peaks are water. There's water here, water here. a big ozone peak here, very obvious carbon dioxide, methane, even more carbon dioxide out here. So by looking at these different wavelengths, looking at the atmosphere of only the extrasolar planet, we can start to decode their atmosphere, and we can pick out what molecules and what chemicals and elements are in that atmosphere. So which one of these planets would make a good place for humans? Or better yet, possibly aliens? All right, let me just see if I want to make sure I didn't miss anything. I don't think I did. So and hold on, I'm getting carried away here. All right, let's try that again. So what do we want to do with the Webb telescope? Well, we want to take pictures of the early galaxy. So this is the Hubble Deep Field. We want to take a Webb Deep Field. Galaxies. We've taken lots of really cool pictures with the Hubble telescope, but it's time to go deeper. It's time to see more detail. And as we mentioned already, we should be able to see more information about individual stars at parts of their lifetime that we normally couldn't see because they're obscured by dust. And we also should be able to pick out some of those extrasolar planets. So there's just so much opportunity out there. Okay, so this is the numero uno image. This is the one they released a day early on the 11th. And again, you can tell which ones are stars because they have those telltale diffraction spikes. And this is a typical picture from the James Webb. And the idea was to take it kind of similar to what we did with the Hubble Deep Field. But the other thing that's of most interest are these arcs. So the things that look like strung out galaxies, perhaps. And what they did was they studied them spectroscopically, and they discovered that many of them are from the same object. So way, way, way off in the background is something, probably a quasar, that is glowing, and the light from that quasar is passing through this galaxy group. And as it passes through the galaxy group, galaxies, the mass in galaxies actually cause the light to bend. And so that's where these arcs come from. And depending on which side of the galaxy it goes, we may see a different arc. And so this is just an incredible picture. And when you look at this picture, just like the Hubble Deep Field, every speck of light out here is a galaxy or a proto-galaxy. And there are thousands and thousands of them in this picture. The neat thing is, for the Hubble telescope, the deep field took weeks of time to capture. And I don't have it in front of me, but if memory serves me right, this image was captured in 12 and a half hours. So not only do we get to see more, we get to see better, but we're also getting to see it in much less time. And that means if we take longer, we'll see even more information. So this is SMACS 0723. And the primary purpose of this image are those arcs. That was the big thing that they were looking for. It's called gravitational lensing. Okay. Then the following day, the 12th, the official day of release, they released 4 more images. This is not really an image, but it's data from an image. This is atmospheric composition of a exoplanet. So this is WASP 96b. And if you look at this, they can decode it and they can say, all right, based on the data, which is a little bit scattered, we use this blue line to best fit what we think we're looking at. And then based on that, they look for telltale signs of different chemical elements and compounds. So you got water here, you have water here, lots of water in this image. And those peaks tell us this planet has water in its atmosphere. I'm sure it tells them a lot more than that, but that's what they're showing us in this picture. So pretty impressive. And if you look at these frequencies, so it's showing them in microns, and of course, most of us think in terms of nanometers. But again, you're in the infrared, so you're longer than normal visible light. Okay, the next one is one that really impressed me. This is the Southern Ring Nebula. And this is taken in the two different ranges, so near infrared and the mid infrared range. And what you see in the near infrared is all kinds of detail in these dust clouds that are billowing out from the star. That's pretty much that one, that it's a planetary nebula. So it puffed off the outer shells. This is what the sun's going to do in 5 billion years or so. All right, well, this is cool. Lots of information, lots of very specific detail in the cloud and its formations. But when you look in mid-infrared, you see, okay, well, there's the star. But you notice it has a companion. And what's neat about this is, all this time we've thought, oh, yeah, this is just a star that puffed into a planetary nebula when it ran low on fuel. But in reality, it's part of a double star system. So it actually has this other star next to it, and they're sharing material. So this other star has not reached the end of its life yet. And it gives us an opportunity to discover all kinds of things about this process and the relationship between those two stars that we've never seen before. Another thing that has been pointed out to me in this picture, it's not that big a deal to me, but maybe it should be, is this is a galaxy out here, this streak with a bright spot in the middle. It is also over here in the mid infrared as well. And so, that galaxy is something that we have not noticed before in our regular pictures. And now all of a sudden it's pretty obvious. Okay. This is Stephan's quintet. I imagine some of you have tried to image this. And of course, in visible light, it's impressive. But the minute you start looking through some of that dust and gas and looking in the infrared, you can see lots and lots more detail. And you can see detail on how some of the galaxies are very clearly interacting. There are streams of stars coming out of the galaxies, and just lots of information that's not really that prevalent in the normal visual part of the spectrum. So that was it for the first 5 pictures. They made a big deal of that. It was frustrating to me that they didn't tell us what their first target was going to be, because I work with the Astronomical League and we would have made an observing challenge relevant to that. Instead, we did it for that star that they used to align the different segments of the telescope. But anyway, moving on. So this was all very exciting. And then, oops, I missed one. Sorry about that. I'm embarrassed. Where's my notes? Okay. This is the Carina Nebula. And again, it's the same kind of thing that we see in a visual image, except you see lots more detail. You see a lot more stars that are actually in here that in a visual image would be obscured by dust. Just amazing pictures, amazing detail. All right, now we'll go on to the next one. So we ought to take a look at Jupiter. Jupiter's kind of important, and Jupiter's moons. And so in these pictures, you can see, you can see the different moons, Metis, Europa. I'm going to mispronounce this, Thebe. So different moons around Jupiter. You can see some detail as well. And these are images that it took of Jupiter. And these are not what I would consider the high quality ones, but amazing detail. It can see the ring, which is actually in both of these pictures. And that to me is amazing because we've never seen that with a visual telescope. So that's really impressive to me. But lots of information. And then the next one, which I find really exciting, is this one. And it's sitting here cycling. I don't know how many times it will cycle. But what we're looking at is this round dot that's pretty much not moving. And note that the stars in the background are moving. And so one of the things that they had to be able to do with this telescope is they had to be able to track something that's moving. Stars are easy. They're not moving. So once you hit a star, you should be pretty good. A little adjustment for your own motion, but you've pretty much got it and it's not going to move. What they wanted to do was be able to track Mars. And in order to be able to track Mars at its fastest speed, you need to be able to track it at better than 30 milliarc seconds of movement per second. This is an asteroid, and it was moving at 67 milliarc seconds per second. And I'd say they did a pretty good job of tracking it. So that's better than twice what the specifications were. So power to them. This is asteroid 6481 Tenzing, in case anyone really cares. But that means not only are we getting these incredible pictures, not only are we seeing through the dust and clouds because of the infrared, but the telescope is performing like a champ. It's tracking stuff that's moving twice as fast as what it was designed to do. So that's pretty impressive. Okay, and this is the latest one that I've heard about. They could have released another one today and I may have missed it, but this is the Cartwheel Galaxy and friends. And you can see why it's called the Cartwheel Galaxy, because it has all these spokes in here. And this is the galaxy is very busy star forming. And so this ring out here, it's a ring galaxy. The ring is actually a star forming region. Plus it has all of these, we'll call them arms, that are also doing a lot of star forming. And star forming tends to be on the cooler side, right? Red, infrared. Not glowing and not up there, giving off all of the different types of radiation you get from full-blown stars. And so just lots of detail here. And of course, you have the same detail in these other two galaxies that are over here. It's kind of amazing. So as far as I know, this is the latest picture, but I know that they're continuing to take pictures all the time. And which brings us back to here, does anyone have any questions? And I'll just mention before we get into the questions and answers that website that's on the bottom, and I'll leave it on the bottom. That's the website to go to if you want to look at their images. And at this point, they have lots of images of the rocket and the telescope itself as they were putting it together. Eventually, it'll be just overwhelmingly filled with new images from the telescope. Okay. So that's it for me. I will mention one other thing, and that is we saw all these really cool color pictures, but keep in mind, infrared is a color we cannot see. So those colors are not what it would look like to us. In fact, to us, we wouldn't see that detail at all. What they have done, though, is they've said, okay, well, this is how we do visual colors. We're going to do the same thing in the infrared where the colors represent different frequencies. The problem is infrared is a lot wider than visible light. So each one of those colors represents a lot more range of frequency. Okay. Are there any questions?
Hi, Aaron. I'm sorry. Someone earlier asked a question in the chat about the micrometeorite damage that had been reported to the telescope and whether or not there was any new news on that. Can you share anything on that?
So I know of no new news. I'll share with you what I do know. The meteorite was bigger than they were expecting. They knew they were going to take hits from micrometeorites. You're out there in space, they're everywhere. You're going to get hit by some of them. And so it was part of their expected protocol that, we're going to get hit. It was bigger than they expected. It did do a little bit of damage. And it is not impacting performance hardly at all. The way to think of it from our perspective is if you're out using your telescope and there's a speck of dust on your primary mirror, that speck of dust is not going to do anything to you in the long run. Yeah, it's taken away a little bit of light, obviously, but it didn't cause any serious problems.
We had a question in the chat from Mark Thompson. I thought the main reason for infrared was the Doppler shift of light from receding galaxies versus seeing better through dust. Any comment on that?
Both. So one of the main things that you get from this telescope and seeing in infrared is that light, which used to be visible or higher up in the spectrum. As it gets further and further away, it's moving faster and faster away from us, and therefore it is getting, I'll use this term loosely, redder and redder. And so it moves into the infrared. Some of it has moved so far that's in the radio, and we can already get that with our radio telescopes. But there's this big swath of infrared where we are confident there are stars and galaxies and stuff out there that we can't see because it's beyond the visible part of the spectrum. So absolutely, that's one of the big pluses.
Mark Gordon asked, why do they orbit the L2 and don't stay still? I think you covered that. So,
well, let me say it again just to make sure everybody caught it. If you were in the L2 location, you would be directly behind the Earth, which means the solar panels would get no light, so the telescope would get no energy, and eventually it would just die. So you have to be far enough out that you're outside of the Earth's shadow so that you're getting sunlight. You also have to be far enough out that you're outside of the moon's orbit because you don't want anything to interfere with communications with the Earth. So you have to be able to point your antenna at Earth at any time.
Then Gerald Klein asked, I suppose due to the location of Webb versus the sun, that there are seasons to what can observe. Are there upcoming targets to be excited about as Webb moves through these seasons?
They're being very cagey about what they're going to take pictures of. So in general, ultimately, a year down the road, all of the images it takes will be public domain. It's a public telescope. The people who are doing the individual research do get a year's head start on the rest of us. So a lot of the images will be put away for a year. We won't get to see those. But they're also not telling us what those targets are. Just like pre-release day, they weren't telling us what the targets were. And so what you're asking is absolutely correct. Just like if you think of midnight, just like at midnight, every night of the year, you see a slightly different piece of sky. Well, the same thing is true for the telescope. It can point in more directions, just like you can point essentially horizon to horizon. It can do the same thing. But there are going to be different fields that it's going to see as the different seasons go by. So, yeah.
I think you mentioned this near the end about the micrometeoroid. What's it? Can you repeat what you said about the damage or uncorrectable damage? Or
well, it's not correctable because we can't go out there to service it. And as far as I know, the only correction for a mirror segment that is significantly damaged is to replace it. Well, that's not an option because of where it is. We cannot get to it. And so the segment that is damaged, and I did know which one it was, I just can't remember. The segment that was damaged, picture it like a piece of, like a glass window that has a bullet hole in it. So you have a little hole, you get a little bit of, weirdness going on near the hole. But in general, the rest of it is perfectly fine. And so as far as I know, they are still using all 18 segments. But if it were a problem and got bad enough, they would just stop using the data coming from that particular segment.
And Don Anderson also said that Forbes magazine has reported that Halley's Comet could damage the Webb as well. I haven't heard that one yet.
Okay. So we, the Earth, do travel through the dust trail left behind at Halley's Comet, as we do for about 10 other comets, or I guess it's probably 8 other comets. And those dust particles are what make the meteors. So obviously they're impacting the Earth. Anything that the Earth is going to go through, this telescope's going to go through as well. So I'm not sure what their plans are. I am confident that they've got some kind of plan that says, okay, if it gets real bad, we're going to turn it so that this incoming stuff's not going to hit the mirrors. But I haven't heard that. That's me suppositioning. But yeah, so not the comet itself, but the dust from the comet, I could see being certainly a problem.
And then Mark Thompson asks again, if the light is redshifted from stars moving away from us, is the light UV shifted from stars moving rapidly towards us?
Well, the answer to the question is yes. I would have said blue instead of UV, but yes. So if you're moving toward us, and I'll give you an example, the Andromeda Galaxy is moving toward us at a very quick rate. It'll be here in about 3 billion years. I'm not going to worry about it because I won't be here. But the light coming from the Andromeda Galaxy is blue shifted. Now, to you and me, it's not blue shifted enough that we can even tell. So most things moving toward us are not moving fast enough to have significant shifts in the direction toward UV. Whereas the universe, because you can go 13.8 billion light years out, as you go out further and further, some of those galaxies are moving quite rapidly. And so the most distant stuff out there has shifted to the infrared.
Okay. And Debbie Moran asks, how are the colors in the images generated? According to relative temperature and analogous to relative temperature in the visible spectrum?
So I got to think about how I answer this. So I would say yes, it works exactly the same. So she's referring to temperature, and I know why she's doing that. I would refer to it as frequencies. And so just like different colors to our eyes represent different frequencies, different frequencies in the infrared represent different sections, and they choose to show those to us as colors that we can recognize. If they showed it to us in infrared, we wouldn't be able to see it. So they have to use colors we can see.
And then the follow-up.
Go ahead.
To follow up with that, how does the color assignment change from the Hubble palette to the Webb palette?
Well, they're all unique. Okay. So I don't have a good answer for exactly how it's different. But we're looking at different parts of the spectrum, and therefore the different colors have to represent different pieces of that spectrum that the telescope is looking at. So Hubble actually had its own color palette as well. So the pictures don't look like real pictures in reality because the color's not quite right. But the Hubble infrared, they have to show us what that infrared looks like. So they show it to us in colors that we can recognize and appreciate. And I'm pretty sure they're doing all of these in the same order. So red is the longer wavelengths, blue is the shorter wavelengths, and they've just shifted them into the infrared or different parts of the infrared.
And Gerald Klein asks again, why aren't there diffraction spikes on every source of light? My thought was that they're just not bright enough. But
so you can get diffraction spikes on very bright objects like galaxies, but it's uncommon. And the reason for that is, well, the easy way to think of it is a star, no matter how good your telescope is, that's not true for the space telescopes, but in general it's true, represents 1 pixel. And so it's the same reason why on a dark night, you go out there and the stars might be twinkling a little, but the planets are not twinkling at all. That doesn't happen every night, but it happens often. And that's because the air is not perfectly stable. And so as it moves 1 pixel up or 1 pixel down, a star looks like it's moving or twinkling. A planet doesn't do that because even though to our eye, a planet doesn't look any different than a star, in our brain, that is, the reality is it's more than 1 pixel. And so if it moves up 1 pixel or down 1 pixel, we don't notice it because most of the pixels stay lit. So the same kind of thing is happening when you get diffraction. So when you have a sharp edge, when light goes past that edge, it tends to bend and you get a diffraction from it. And that's what causes the spikes. In a typical earthbound telescope, if you're using a Dobsonian or a Newtonian, you'll see 3 spikes. And the reason for those spikes is 3 veins. Or if you have 4 spikes, it's because of 4 veins. And so when you look at the Hubble, it has 4 veins. That's where those spikes come from. But I think it's the same thing, or the same kind of concept. The stars, if they were 1 pixel, have to be affected by that vein. But if it's a galaxy, it's bigger than just 1 pixel. And so you get a little bit more blending. And so you tend not to get the spikes. So that's Clevenson's opinion. Don't quote me on it.
Okay. Kate Robertson asks, why is it we can look in any direction and still be looking back towards the Big Bang? Shouldn't the redshift be coming from one direction? One point, there was the location direction of the Big Bang. Why is this effect the same even if we look 180 degrees in the opposite direction?
Great question. You said Kate, right? Good job, Kate. Excellent question. If you think about the universe and you subscribe to the Big Bang theory, scientific theory, that means the universe as we know it at one point in the past, about 13.8 billion years ago, was very, very dense, very, very compact. And when the Big Bang happened, the easiest way to think of this is a singularity. I happen not to believe that, but that's okay. So if you think of it as it's a point, and that point is where the Big Bang happened. So if you ask the question, where did the Big Bang happen? The answer is everywhere. So this is one of those weird physics concepts. Because as the universe expanded, that point is now represented by every other point in the universe. So, and I know for a fact my daughter thinks she's the center of the universe. So I know this is a fact. So, okay, I shouldn't say that. Anyway, so that's the first piece. That's the concept that the center of the universe is everywhere. That means every point in the universe is expanding away from every other point in the universe. So everybody's moving away. So it doesn't matter where you are, no matter where you look, everything is going to look like it's moving away from you on the grander scale. And so, yeah, you're absolutely right. We can look 13.8, I'm going to try to do this on the monitor here, 13.8 billion light years that way. We can look 13.8 billion light years that way. So we're actually seeing twice as much space as we should because of the Big Bang, right? It was only 13.8 billion years ago. But that also explains why we can't see any more, because that's as far away as the light has had time to reach us. So did I get it, Kate? Let me know if I need to go into it in more detail.
Could I jump in with a typical analogy that's given of either raisins and expanding bread or dots on an expanding balloon, that there's no central dot from every single point, everything else is moving away, and the farther away it's moving, the faster it's moving away, no matter which raisin you choose or which dot on the surface of a balloon you choose.
Right. Now, if you use the balloon analogy, those are both great analogies. Thank you, Debbie. But if you use the balloon analogy, we're talking about the surface of the balloon. Whereas if you're doing the raisin bread analogy, it's the actual bread because it's expanding in all dimensions. But yeah, those are excellent.
Mark Thompson asked, did NASA rotate the Southern Ring Nebula photo on purpose so it looks less like a face? I didn't notice.
Well,
I've never seen the Southern Ring.
Well, neither have I, but keep in mind, there is no up in space. So however they want to show it is perfectly fine. But I understand it may not be the typical way it's represented.
Let's see here. Let's see. Dawn put a link in there. Is this still information correct from 2016? Dawn, can you come off mute and ask what you're talking about here?
So I'm going to stop sharing just so I can see everybody.
Okay. Hi, Aaron. It's just a link that I've had from a long time ago. And I like your Star Trek background, by the way. That about the Hubble false color. And that obviously a lot of that is added. And you kind of touched on that earlier, so we would recognize the colors.
Yeah, and that's a problem for a lot of people. You know, we think visible light because that's what we can see. And we see all these really cool pictures from Hubble or now from the Webb. And it looks like visible light because they're showing it to us in visible light. But that's not what their sensors are detecting. Their sensors work just like the Hubble would in visible light, except it's a different wavelength. It's looking at infrared light.
Mm-hmm.
But, you know, it works exactly the same way. And the colors are just there for us. Right. You know, if you are some of you, I'm sure are into astrophotography, we have all kinds of filters at the observatory we use. We have the typical RGB, red, green, blue filters that we use, that if you use them, you still have to process it, but basically it'll capture color pictures for you. The problem is that's only one set of filters that they use. They also use one that's, let's see if I can remember what it is, sulfur 2, oxygen 3, and hydrogen alpha.
Yeah.
And they combine those using the exact same tools that I would use to do my color pictures. And you get color pictures, but it's not real color. Or at least not a proper representation of it.
Yeah. Okay. I kept that article from a long time ago. Whereas the I might not be completely understanding this correctly, but the Webb gives off a more chemically correct color version in the picture, doesn't it? Of the elements in the picture.
But it depends on what you mean by that.
In the infrared.
Well, yes. I mean, it gives information, but
Right.
you have to kind of forget the idea that those colors aren't real colors.
Right.
Or at least colors as we know them. By the way, Mark, I like your image that you're showing us there.
Thank you, by the way.
Oh, thank you.
Okay, next. Robert Stein asks, is Goldstone the only deep sky network antenna being used? If so, are the images stored on board the Webb?
So the answer to the last question is yes, it can store pictures, because you never know when you're going to lose communications and you don't want to lose the pictures. So it has storage capacity. But the answer to the first question is no, it's not the only one. They have a deep space network that they're using. And so no matter which way the Earth is facing, there's a telescope, a radio telescope pointing at the Webb, or at least at the times when it needs to.
Okay. Jerry Geidesick, pardon me. How are the Langrian locations calculated?
Okay, so I'm going to pick on you, Steve. You just massacred Lagrangian, but that's okay.
Sorry about that. Yeah.
They are points of stability between the two gravities, the gravity, in this case, of the Earth and the gravity of the Sun. So the one that's between the Sun and the Earth, I'm sure it has to do with the masses. I've never calculated them, so I'm not directly familiar with how it's done. The one on the opposite side of the Earth is counterintuitive. This is the L2, the one that Webb is at. It's counterintuitive because wouldn't you be pulled on by both gravities? And the answer is yes. It's still a stable point, though. As far as when you're going a certain speed, you're orbiting the Earth, it works. The L4 and L5, that's the one in front of and behind in the orbiter, are actually fairly easy. They're 60 degrees ahead, 60 degrees behind in our orbit. So, you can determine exactly where that is. That's easy. And the one on the other side, which ought to be L5, 3, I don't know, whatever it is. I'm not looking at the picture. The one on the opposite side of the Sun is also easy to calculate. It's exactly where the Earth would be 6 months later.
Okay. Steve Merriman asked, does the infrared sensors require cryogenic cooling? Does this impact the operational lifetime of the instrument?
Yes, absolutely. And this was a problem with the Spitzer Space Telescope, is it ran out of cryogenics. And once you don't have the cooling fluid, you no longer can cool the instrument, and therefore you can't do the science that you intended to do. So yes, it is cooled. It is cooled to some ridiculously cold value. It's in my notes, but I skimmed over that during the presentation. But it's something like 5 degrees Kelvin. Again, don't quote me on that, but that's the neighborhood that it's in. And very, very, very cold. And so that tells me they must be using liquid helium, just because it's so cold. I don't know that for a fact either, but that's what it implies to me. And yes, when it runs out of that liquid, and I'm going to assume it's liquid helium, they will no longer be able to cool the telescope. They can still do research. The Spitzer telescope went on for years beyond the point where it lost its coolant and was doing other types of research, just not with the same accuracy.
Question from Jerry again is, with all the different groups using the telescope, how do they divide up the time between all the different groups that need access?
So I'm not really sure. I'm not part of that panel, so they never asked me my opinion, so I don't really know. But typically what they would, and of course this is brand new, right? Brand new telescope. So I'm sure the people who kicked in the most going into this would get higher priority. I'm also fairly confident that they probably looked at what your proposal was, what you want to look at, and decided how that best fit in as far as packing as much observing as they can into a short period of time, and also which will have the most value scientifically. So again, I'm not privy to the details of how they did that.
Joe Dellinger says the mirror cannot move with respect to the solar shield, can it? He's got several things here. So answer that one. Mirror cannot move with respect to the solar shield.
So my take on that is that's correct.
Okay.
I think that it's a fixed mirror. And what they do is they reorient the whole spacecraft. Keep in mind that that heat shield is the size of a tennis court.
Right.
So it's gigantic.
And then he says, so the telescope can't point directly away from the sun either, can it? It has to point about 90 degrees away from the sun. Question mark.
So ideally, you would get the most, let's say, shade from your sun shield at 90 degrees, just looking at how it's designed. And I think you're probably absolutely right. It can't look directly away from the sun either. Unless all of this is based on a false assumption.
Yeah. Okay. Bob Ferry says, if I understand early analysis, it appears that there are many more galaxies and heavier elements in the early universe than expected. Your comments?
So I know what I've been taught. I know what I teach. And I'm thinking about how the best way to respond to that. So the first stars had to have been formed out of hydrogen and helium because that's all there was, according to the theory. So they had to be extremely huge stars, massive stars. In fact, it's possible we will, well, now that we have this new telescope, maybe we will, but in general, the idea was we'll never see those stars because they would explode almost as fast as they would form. So the hydrogen and helium would form. They're so massive that they would just blow themselves apart. So when that happens, supernova, you would get heavy elements, and those heavy elements will go out and seed new stars. And so you get more and more heavy elements as time goes on. So the earliest stars would have had no heavy elements at all. That next generation of stars would have some heavy elements because they're just out there floating around. So when you form by all this stuff collecting, you're going to pick up some of that heavy stuff. And then the generation of stars we're in today, they're actually called population 1 stars. Those are the ones with a good proportion of heavy elements. So that's everything, in essence, everything beyond helium. So when we're looking back through this telescope, what we're seeing is back as far as it's going to let us see, which we're hopeful is very, very, very far back. And what we're looking for has to be bright enough to be seen. So that's one of the criteria here as well. And so once you form into a galaxy, you're now bright enough to be seen. You already have gone through a few generations of star forming, so you should already have some of those heavy elements. So I do not think it's correct. I have not heard anything to make me think otherwise. I don't think it's correct that there were more heavy elements than we expected. But I've also not seen the analysis of, okay, this is what we're seeing, and based on the timeline, this is what we should be seeing. So I have not seen that analysis.
Okay. Mark Gordon asked, does the James Webb always use the same magnification?
I'm thinking.
I would think because there's no real lens.
Yeah, there's no focusing mechanism. So yes, it is the magnification it is looking at. And if you're wondering how big a piece of sky this would be, I've heard it said a couple different ways, but if you hold a, let's say, index card out at arm's length and you put a pinhole in it, that's how much of the sky it sees, what you can see through that pinhole.
I've heard something like a piece of sand behind your fingers at arm's length.
Well, yeah, well, that's about the size of a pinhole. So, yeah. Okay. Yeah, I heard the sand one as well.
Okay. I think that's about does it. Does anybody else have any questions? Come on off mute and chime on in.
Those were all excellent questions. It makes me wish I was part of the team so I could actually answer them with the knowledge that the team members would have. Yeah, Mark Thompson, I see your picture there. Looks interesting.
Anything else?
I'm going back to actually compare. Yeah, it does kind of look like in these pictures, an upside down face.
Mark drew in some eyes in there. Anyway, anything else, people? If not, I'm going to close it on out and hope to see you all either virtually or in person at our next September meeting.
Thank you all. It's been a pleasure.
Thank you, Aaron. Very good. Very good.
Thanks, Aaron. Thanks, Steve.
Okay.
Good job.
Thank you. Thank you.
Hey, Aaron, I just had one quick one.
Yeah.
Yep.
The linear progression, 13.8 billion years ago, all measured by, how many laps a very small planet in a very small place in a very big universe. Are they working on time? Is there a better time notion than measuring this entire unbelievably big set of objects on this insignificant planet, and how many laps it takes, how much time we think it takes to get around the sun? Are they working with time? Time and space contract, all these different relativistic things. How does that play into the physics and how they're looking at this?
So on a local scale, we know that time can change just like space can warp. So, there's all kinds of weird effects like that. And of course, any trip you take as a light particle through space is going to be affected by all the gravitational wells that you pass near or by. So as far as I know, no, nobody has taken all that into account other than we're looking at the average. The thing that I find interesting is if you think about space, the universe, we tend to look at it. We went through this big thing with Galileo, basically, that said we are not Earth-centric. We are, in our case of our solar system, sun-centric. And that's true. But if you think about the way we think, we are all Earth-centric. So for us, living here on planet Earth, where a year has a specific meaning, looking at distances as far as light years makes perfect sense, because the speed of light is a standard. Year, that's Earth-centric. That's coming back to how long does it take us to go around the sun. But it's all relative. So there is no absolute frame of reference. So that time reference is as good as any other time reference. Not a good answer, but that's my take on it.
Well, I think time is well specified. I mean, it's like a certain number of vibrations of some certain mode of some certain cesium atom, and so if some aliens might define time a different way, but I think according to current physics, we could just scale it, and we'll come up with the same physics.
Yep, I think that's true.
Sounds Earth-centric.
It is. But how can we be anything else? We're Earthlings.
I thank you. I guess it's time to be quiet.
Okay.
All right. Well, I'm going to sign off then.
Thank you, sir. Thank you, Aaron.
See you all later.
Take care. Everybody else? If not, have a good weekend. Watch the heat. Stay hydrated. Be safe. We'll see y'all later.